Hi, everybody, and welcome back to our next video. So today's topic is on rates of change. So today's video is really going to focus on applications of these derivative functions and how we can take real-world situations and apply this calculus concept to them, and then how we interpret those results. So if you remember back from the beginning of the course, back in Unit 1, when we differentiate a function, we're calculating the change of our output variable as our input variable changes. Again, we can represent this a whole bunch of different ways. We can say that it's delta y over delta x. Again, Newton and Leibniz each had their own notation, dy dx or f prime, but they all just represent that same concept of we're looking at the change of our outputs relative to our change in our inputs. So this means the value of a function's derivative at a particular input value is also referred to as that instantaneous rate of change at that particular value. So this means that any quantity that we define as a differentiable function can have its derivative's value described as a rate of change. So when we think about real-world quantities, this takes on a really important application, and we can apply it to a lot of different scenarios. The concept of derivative functions are used in all kinds of STEM-related fields. Physics is our main application. Newton created his system of calculus to help him explain his system for the physical universe. So it has direct correlations into a lot of stuff seen in physics, but it's not just used in sciences. Business courses that you may take in college or economics courses, if we have a function that represents a company's profits, we can actually look at the derivative to see how those profits are expected to change given different variables that are reported into the function. So there's a whole bunch of different ways that we can interpret these. So we look at a lot of different scenarios in this section. But for all of these, when I have this quantity defined as a differentiable function, we're going to call it f of x, then its derivatives values, so f prime of x, those functions' values or output values can be described with the units of this ratio. So we take the units of f of x, so the original function, divided by the units of x, and that is our output value for the derivative function. So one way to think of this would be if f has points x, y, then f prime has points x. So again, it's still referring to an x value on the original function, but then those output values are the y units divided by the x units. So, and if we were to continue on and we look at the second derivative, so f double prime, they would have points of still the same inputs, still the same x values, but now we would be looking at the change in this guy, so the ratio of the y over x divided by that x again. So we can continue this process on and on and on for however many derivatives we can find for a given function. So this concept of being able to apply the calculus and interpret the meaning and units of a derivative's value, it's a really, really important part of calculus, because if we can't apply it to the real world, then there's not a whole lot reason to actually be doing and learning the math. So we're going to take a look at a few different examples here of just calculating the value and then interpreting it. So for this first one, it says the number of gallons of water in a storage tank at time t in minutes is modeled by the function w of t equals 25 minus t squared for the interval of values 0 to 5 for t. We want to find and interpret w prime of 3. So before we actually do the calculus, I just want to kind of analyze the information that's given to us. So we have this original function w of t. So for this function, our points, our inputs would be t, our outputs are w of t. But then I want you to consider the units used for this guy. So they tell us that t is measured in minutes, and that our w of t is representing the number of gallons of water in a storage tank. So that means our outputs are measured in gallons. So what this function is describing is at a time t, there are blank gallons of water. So if we were to find the value of the original function, say at t equals 3, then what that function produces is this information. It's going to tell us at that exact moment in time how much total water is in that storage tank, which if the function for w of t is not a constant function, that means the amount of water must be changing somehow. So whether it's raining and it's collecting water, or we're pouring water in, or a hose is filling it up, whatever it is, the amount of water in that tank must be changing. And if it must be changing, that is like saying that this real life quantity is differentiable. And that's an important part of this. So to understand that a quantity, a real life quantity, is changing is just like saying that the function that represents that real life quantity is differentiable. And if it's differentiable, then we can do our calculus. We can find the derivative equation and substitute this value in. So now let's analyze what the derivative function would be. So its name would be w prime of t. Their points would be represented by t and w prime of t. But then our units, again, our inputs are still t, so it's still measured in minutes. But now this output is a change in w as t is changing. So now we have to have a rate of change. And again, a rate of change is a comparison or a ratio of two quantities or two units. And it's always going to be the output of the original divided by the input of the original. So the units for this derivative would be gallons per minute. And again, if you just think about what the derivative is telling us is at time t, the amount of water is changing. So I'm going to put this in quotes because changing is not really going to be the best word once we actually have a number, because change is kind of ambiguous. It doesn't specify whether it's increasing or decreasing, but once we have a value for the rate of change, then we'll actually be able to describe that in a little bit better detail. So changing somehow for right now at a rate of blank gallons per minute. So that is how we would go about interpreting the value of w prime of 3. So that's really our end goal here. We want to take the derivative, substitute 3 in, and that value will be able to answer this question. So let's go about doing that. So if w of t is 25 minus t squared, then w prime of t, just taking the derivative, it would give us negative 2t. So now for w prime of 3, I would get negative 6. And again, I can go ahead and slap these units on here, negative 6 gallons per minute. So now we have to think about what that value means in context. So we're basically just rewriting this sentence, but to save me a little bit of time, I'm just going to erase and rewrite. Oh, apparently Cami did not like that. So let's just get rid of this guy and we'll rewrite it. So at time 3, now at time 3, that doesn't really sound all that nice. So, okay, apparently we're just going to rewrite the whole thing. So we could say that after 3 hours, so again, when t equals 3, that means it's been 3 hours since the beginning of us tracking this, but after 3 hours, the amount of water in the tank is, so this is where we want to describe the kind of change we see. So this is a easy enough process. When our rate of change is negative, that means that the amount of gallons in the tank is decreasing every minute. That's how we interpret those units. So when it's a negative rate of change, the original quantity is decreasing. And when it's a positive rate of change, the original quantity is increasing. So it's pretty straightforward. Negative going down, positive going up. So in this case, we know that it is decreasing. And then we can be more specific by saying at a rate of 6 gallons per minute. So knowing that the amount of water in the tank is decreasing, that must tell us that there's something going on. There's a hole in the tank, or it's purposefully being let out, but somehow the total amount in the tank is decreasing for that given moment in time. Now, right after t equals 3, it may be changing at a different rate, but again, without it being an unnatural change, we know that it would still have to be decreasing. If we wanted to increase, we'd have to slowly approach 0 as our rate of change, and then we can go towards the increasing rates. But this is just one application, one way that we could take a real life quantity, find that value of the derivative, and interpret it. And again, it all comes down to these units. So a lot of these problems, you're going to see me write out these ordered pairs with the units for our inputs and our outputs, because it helps visualize, it helps you to see exactly how we interpret the values of these derivatives. Okay, so let's try another one. It says the temperature in degrees Celsius of the water in a pond is a differentiable function W of time t. The table above over here shows the water temperature as recorded every 3 days over a 15-day period. We want to use the table to approximate and interpret the value of W prime of 12. Well, to find the exact value of W prime of 12, we would have to go through the exact process that we just did. You have to have an equation or the graph of the original function. Just having a table of values will not tell us the full picture and will not let you actually do calculus. You have to know the exact equation or the exact curve to actually have a chance to do the calculus and come up with the exact instantaneous rate of change. But if I want to approximate instantaneous rate of change, remember that that is equal to the secant line slope. So if we want to estimate the slope of the tangent line, we use the slope of the secant on an interval that captures the value that we are interested in. So there are a few different options here for what interval we choose, but we want to choose the one that is most appropriate. And in this case, there's actually 2 good candidates for approximating this rate of change. So again, this would be slope formula. We got to pick 2 points that the curve of W will pass through, and that all these different pairs on this table represent these different points. So then we have to choose an interval that actually includes t equals 12. So to do that, I mean, there are a bunch of different options. We could go from 0 to 15. 12 is in there, but there's a lot of unnecessary values, and it might not tell the most accurate approximation. We could do 6 to 15. That's a little bit closer. We could do 9 to 15. That puts 12 right smack dab in the middle, but it's still a longer interval than what's necessary. So the best candidates would either be from 9 to 12 or from 12 to 15. Both of those include 12. It's okay that it's an endpoint, and they're the smallest interval that contain 12 that we can actually choose. Both of them are equal length of 3 days. So there's really no way to discern which interval would be better than the other. So it's really a matter of choice. You could find both and then maybe look at both to see which one would be more accurate. In this case, I'm just going to pick 9 to 12. Again, that's just arbitrarily picking. It's not a huge deal here. So before we fill out this slope, though, let's review our points. So for W, my input are t values, and those are measured in days. In this case, it's measuring time in days. And then my output values are the degrees Celsius, so our temperature. So then for W prime, we should end up with a ratio of the inputs and outputs. My inputs are still days, but then for the outputs, we would get degrees Celsius over days. So even when we approximate, we should still end up with this kind of ratio of units for this end result. So let's just keep that in mind as we set this up. Identifying the units ahead of time, especially for these average rate of change problems, which is what this is because we're approximating, can really help us, because sometimes there's an issue of what functions values go in the numerator when we're setting this guy up. But if I do need to end up with this ratio, then seeing that it's a fraction, these have to be degrees Celsius values. So if I'm choosing the interval from 9 to 12, this fraction would set up to be W of 12 minus W of 9 over 12 minus 9. Again, just slope formula. So rather than plugging them into an equation, we're just picking out values from the table. So we have 22 according to the chart when t is 12, and when t is 9, we have 24 over 12 minus 9. So we get -2/3. Or when I apply my units, that means I get -2 degrees Celsius every 3 days. So that's one way to leave it. We could leave it in those terms, but that's not really an easy way to express this. So another way of saying this is we could divide top and bottom by 3. So what that gives us is -2/3 degrees Celsius every 1 day. It's still an equivalent fraction. It does look a little bit more cumbersome having that tiny fraction in the top, but what that does is it allows us to provide an interval for that input variable that's a little bit easier for people to understand. Be a little bit more difficult to talk about in terms of every 3 days something happening, but when we talk about what's happening every 1 day, it's a little bit more reasonable for people to truly grasp what's happening. So as far as interpreting goes, we know that the temperature is, or let's see, so the temperature on the 12th day, again, if we look at the sign, it's negative slope, so we know that the temperature is decreasing now, just like last time we want to talk about the rate, but we have to specify here that this is an approximation. Or another way of expressing that is describing it as an average. So we can say it's decreasing at an average rate of 2/3 degrees Celsius per day. So again, it does make the size of our rate much smaller, maybe a little bit harder to grasp that part, but controlling it every day rather than every 3 days does make a little bit clearer gauge for someone to understand this. All right, let's try another one. So this one's going to be special because we're going to use a calculator for this one. I'll explain why here in a second. So a student proposes the function p given by p of t equals 20 plus 10t times e to the negative t over 3 power as a model for the temperature of the water in the pond above. So go back to this guy at time t, where t is measured in days. So what that basically means is someone used a computer device. They plugged in these ordered pair points into a data table, and then the computer or calculator spit back out this model equation as a good and somewhat accurate fit for these data values. So it may not be a perfect fit, may not be a perfect model, but this was an acceptable model, and now we're going to use this to find another approximation. But the only way, or the only reason this is an approximation now, is because this is not the exact equation for the data, but a model. So we are technically still approximating it because it's not going to tell us the exact real world instantaneous. But as long as this guy is a good model for the data and it fits it very closely, then this is a really good approximation. So it's an approximation in the sense that we're using a model, but we are not going to approximate again with the average rate of change process. Now we are going to find the instantaneous rate of change of this model equation. So it's an important difference there between these two problems. So to do this, we're going to find the P of t equation, and then we're going to substitute 12 in. But if I were to do this by hand, so it is possible to do this by hand, but this is not a quick and easy derivative. And even if I did find that derivative, I have to plug 12 into an exponential function. And because of that, no one can calculate e raised to any power except for 0 off the top of their head. So a calculator is going to be required for some of these real world problems. So if that is the case, if you guys have access to a calculator, we can actually ask the calculator to evaluate the value of a derivative function for us. It will actually compute the equation, and then you can tell it what number to substitute in as an input value. So I could do it by hand. It is possible for this one, but it's just going to be kind of cumbersome, and we're eventually going to have to use the calculator anyways. So I'm going to show you guys how to set this up in the calculator. So when we want to find the value, so most of your calculators do not find the actual equation of a derivative. If you have a really fancy TI Inspire, or TI-89. I believe those will find the actual equation for you, but most of us aren't walking around with those because those are pretty expensive. But all of them do have the ability to evaluate or find the value of the derivative function. So to do that, we're going to use a function called nderive, or in your calculator, it'll show up like this guy. So depending on your model of calculator, the older ones, it will pop this guy up on the main screen, and then you're going to tell it three pieces of information: what function it is you want to take the derivative of, what input variable we use, and we will always be using x until we get to calculus 2 and we talk about polar and parametric equations. But for right now, we are always using x. And then the last guy is our c value. What number is it that we want to actually substitute into the derivative function? Now, newer calculators, I'm going to show you guys what that looks like here in a second when I bring my calculator up. But you're still going to be required to tell it these three things, okay? Now, for the function part, you have two options. One option is just typing this exact equation into this spot. But now on paper, we're using t as our input. But again, the calculator has to use the x variable. So we will rewrite it in terms of x instead of t. So one option is to put it in here, but for things that we're going to do later on down the road, I find it really helpful to actually type our function into Y1. Because some of the older models, you have all these extra parentheses and commas and stuff, it can be kind of a pain in the butt to type the function directly in here, and you may miss a parentheses here or there or something. So my recommendation is to actually type the function into Y1, and then we can actually call up this input from Y1 and put it directly in these parentheses. So let's walk you through that process. So here's my calculator. I've got the 84 plus. So again, mine's going to look slightly different from the rest of you, but the buttons are all the same. So I'm going to go back to the main screen. Make sure you guys are on the main screen. Second quit if you're not. And I'm just going to clear everything out. So my first step, I want to go to y equals. Now I have some stuff in here from before, but I'm going to get rid of those guys. Then I'm just going to type the equation itself into y equals. So let's see, we got 20 plus 10. But again, I can't use t, so I have to use the x value. I know there is a t on this button, but this is for different modes of functions. T is used in parametric mode, theta is in polar, and n is in sequence mode. You won't use any of those until later on in calculus 2. So we just change the variable into x when we are doing these problems in the calculator. So then I get e to the negative x over 3. So open parentheses, negative x over 3, close parentheses. So older calculators, you guys won't actually have this up top. It'll be a caret, but then you still open your parentheses and type everything in. Close your parentheses at the end. So our function that I want to find the value of the derivative of is in y1 right now. So as long as that's in there, we can second quit, go back to the main screen. And now the nderive function is under the math menu. So I'm going to go to math. And for most of you, it should be option 8. Different models, and maybe the numbering may be off. I think older calculators may not have this x root option, but find the nderive option. So for me, it's number 8. So newer calculators, this is what it looks like. It actually sets up a ddx problem. So in this little box, we would do the x variable. So type in x. This is where your function goes. So you do have the option of typing the 10 plus 20t e to the negative t over 3 power directly in here. But because we stored it in y1, it makes it a lot easier, because now all I have to do is go to the vars menu, which stands for variables. And we're going to go over to the y variables, which lets us pick out a y equals. And we are currently in function mode. That's why we're using x as the input. So choose function. Then you can just pick any of these guys. So if you have 10 problems to do, you can put 10 different equations in the y equals menu, and then just call up each individual one that you need to. So I want y1 to be put in here. And then my value of x that I want to substitute in goes in here. So in this case, we want to know the value of p prime of 12. So I'm going to ask it to substitute 12 in after they take the derivative. So that is what the newer calculators will look like. If you're working on an older model, you guys would just type those three things in. So by the end, yours will look like this. We'll have y1 in the first slot, x in the second, and then 12 in the last. I'm sorry, tablet doesn't like it when I'm using the calculator at the same time. So 12, and then we hit enter, and it will find us our value. So let's do that. Oh, of course. Oh, I'm sorry. Make sure that you're using the negative button, not the minus. Sorry about that. Let's try it again. And there we go. So good rounding rule, 3 decimal places unless otherwise told. So we're going to go negative 0.549. So P prime of 12 is negative 0.549. Always slap units on there when it's a real world context problem. So in this case, this would be degrees Celsius per day. So this automatically kind of gets rid of the every 3 days issue that we had before. So when we're actually using the calculus, this is always going to be per 1 unit of our input. The only time it's different is when we're estimating with that average rate of change, then we're kind of restricted to whatever this bottom subtraction ends up giving us. So you can kind of tell negative 0.549, that's not too far off from negative 2/3. That would be negative 0.666. So it's roughly less than 1 degree Celsius that we're losing each day in that temperature. And again, this is not the exact real world value because, again, this is still an approximation. But we don't have to use the squiggly sign here because this is the exact value of the model equation that is producing. So what we could say if we needed to go deeper is that this is approximating that actual real world value. We wouldn't know the exact real world value anyways, unless we were able to take data up for every moment in time and track it instantaneously, which we can. And again, that's the idea of why we build these model equations. We collect data, use these programs to build the model equations, and then we can do our calculus with those models. So as far as interpretations go, this would be the exact same interpretation as before. The only difference is we can lose that average now because this is no longer an average. This is talking about an instantaneous rate of change. It's an estimate for the instantaneous rate of change. And obviously our value would change to negative or to 0.549 degrees Celsius per day instead of the approximation from before. Now we're going to take a look at another kind of application. So the first few examples here really focused on like generic real world quantities, so temperature per day, gallons of water per minute, that kind of thing. But like I said earlier, Isaac Newton, he developed this system of calculus to help explain his model of the physical universe. So a lot of our applications deal with that realm of physical motion. So that's what we're going to take a look at for these next few examples. So within the system of calculus, there's really two kinds of motion that we talk about, but they both revolve around motion within a straight path. So sometimes we look at the that change in a horizontal direction, other times in a vertical direction. So that's what we're going to focus on through this unit as we kind of progress the rest of this way. Um, so we're going to be looking at common rates of change throughout this unit. Again, the most common of these describes the motion of objects as they travel in straight paths. And again, that covers both vertical and horizontal. So as we discussed in the past, any object's motion can be described by three quantities. So we have position. So that is describing where the object is at a certain time, t, relative to the quantity of 0. So in context. So is an object to the right of its starting point at 0, to the left, and so on, or is it above the ground, below the ground, that kind of thing. So when we talk about position, oftentimes, depending on what it is it's measuring, either vertical or horizontal, with vertical motion, we tend to use S of t. With horizontal, a lot of times we use X of t. It doesn't have to be that. That's just the common practice when we're talking about this. But then we get into the derivative quantity, so the change of position. So that would be velocity. So the velocity quantity or function, um, and really no matter which kind of motion, we represent that as v of t, or we can think of it as the derivative of s or as x prime as well. But that describes how the object's position is changing with respect to time. So as time changes, as time passes, how is the position of that object changing? So is its position relative to the ground increasing, or is its position relative to the ground decreasing? So getting closer to the ground. So in the realm of physics, velocity is regarded as a vector, which means it gives both magnitude, so a rate of change. So is it a big rate of change or small rate of change? But it also gives direction. So it can describe how an object is moving relative to this null position. So is it going up, down, left, or right? So velocity can sometimes get mixed up with speed. We'll talk about this more here in a minute, but just to preview it, speed is a change in position as well that you probably are more familiar with, but speed does not describe direction, so it's not regarded as a vector. A car has a speedometer in it, and it tells you how fast the car is going, but it never tells you what direction you're driving your car in. It's just telling you how fast your car is moving right now. So speed is the same thing as velocity, but without the direction. So we oftentimes will refer to speed as the absolute value of velocity. We don't care about the sign of that quantity, just how big the number is. Okay. So velocity is our second piece of information, and then acceleration is the third one. So this is if we follow this sequence, acceleration, we represent that as a of t, but we can also describe that as the second derivative of position. So it describes how the object's velocity is changing. So we can think of it as the second derivative of position, but we can also think of it as the first derivative of velocity. So this is also a vector, and so it's also going to describe whether the object's velocity is increasing or decreasing and how quickly. So there are actually more in this sequence. If you go into physics, there is a third derivative in this process. It's referred to as jerk. So that's like when you slam on the gas pedal and you start to accelerate very quickly or make those changes very drastically, you can actually feel it in the car. Your head gets jerked back. So there's a lot more to this in the realm of physics, but in here we really focus on these guys: position, velocity, and acceleration, and these are commonly referred to as PVA problems. So if we take a deeper dive into vertical motion, this one's one, if you've taken an algebra-based physics class in the past, you've done these kinds of problems before. I'm sure you've heard of them or seen some of them in other math classes, but you've never had to apply calculus to the situation. And that's where we're going to go. So when an object is launched upwards or downwards in a straight path, and this launched term can be a little misleading. Sometimes we simply drop objects. We can consider that a launch, but it's an idea of we are beginning to move. So whether that's with force or without force. So did I throw a ball up in the air, or did I just simply drop it off of something? So when we start to change the position of an object in a straight path, and again, this is all assuming that air resistance is ignored. So when we talk about other forces in physics, again, these equations may change slightly, but what we are doing here is we're ignoring all those extra things. So when all of that criteria is met, we can use calculus to describe that motion. So for vertical motion, this is our position function. Every object has this general form. It's read as S of t equals 1/2 a t squared plus v naught t plus s naught. So to break down some information in here, a is our acceleration due to gravity. So there are two common measurements for that, either negative 32 feet per second squared, or a is negative 9.8 meters per second squared. Whoops, don't need two division bars. So it just depends on the units that the problem is referencing. So you guys do want to get familiar with those. But that is the acceleration due to gravity. So every object on Earth is being pulled back down towards the surface. Notice the direction there, that negative. So it's pulling it back down towards the Earth at this rate. So that is the acceleration. So the way we interpret this, if I break the units apart, another way of writing this is feet per second per second. So what this is saying is that if you drop an object, and again, no other forces or air resistance are acting on it, if you drop an object on Earth from any height, every second that passes, the velocity of that object is decreasing, or it's getting bigger in the negative direction because I'm dropping. Um, it's going to travel 32 feet per second faster for every second that it falls, but it's going in that downward direction towards the Earth. Okay. Or another way of thinking about it, if I throw something up in the air, that gravity or that force of gravity is actually what's slowing it down. Because if I throw it up in the air, it would have positive velocity. And so this guy is counteracting that. And that's what makes it approach a velocity of 0 as it reaches its peak. So that is what that A value is representing. In some text, you may see it written as a G for the force of gravity. It's the same idea. It's just a different way of representing it. And then V naught. So V naught is our initial velocity. So that is the velocity at which the object is traveling at the moment of release. So if you drop an object, then your V naught is 0. If we launch an object, then your V naught is not equal to 0. It's going to be whatever the speed the speed and direction at which we are launching it. So if I throw a ball up in the air, then V naught will be positive. But if I drop it or if I throw it down towards the ground, then V naught would be negative. And then S naught, same idea, but with position. So S naught is our initial position, or if we're talking about vertical motion, this would be our initial height of the object. So when an object starts on the ground, then that initial height is 0. But if it's starting elevated in any way, then it would be whatever the height of the object is. So the job of this function is simply to tell you the height of an object at a certain time. That's really all we can do to interpret it. Now, looking at the graph, we can dive deeper and start to talk about, is the height increasing or decreasing? But when we start talking about how the position is changing, that's really a description or interpretation of velocity. But if I simply ask for S of 3 and I get 9, all that means is after 3 seconds, the height is 9, whatever units we're using, just call it feet. That's really the only interpretations or applications that this position function is relevant for. Then we have our velocity function. So again, one name we could use is v of t, so the velocity of the object at a given time. Or again, we can interpret that as the first derivative of the position function. So for vertical motion, a velocity function will tell you how the height of an object is changing with respect to time. So that's the big idea here. So when we go to interpret the values of the velocity function, anytime that we have a positive value, so when v of t is greater than 0, then we know the height is increasing. So again, that's a positive change in the position. So again, if the position was 5 and now it's 10, that's a bigger position, which means we are higher off the ground. The distance from the ground to our object is larger, and therefore it's increasing. And then the flip side of it, if that value of velocity is less than 0, so negative, then we know that the height is decreasing. So same logic, just the flip side. So a good way to think about it is, if velocity is positive, we are moving away from the null position, or that the ground. And when velocity is negative, we are heading back down towards the ground. So then our third piece is the acceleration function. So for acceleration, again, 3 different ways that we can interpret that. The acceleration, we can represent it as a of t, or we could describe it as the first derivative of the velocity function, but then we can also think of it as the second derivative of position. So 3 different notations, all for the same quantity, the same equation. But interpreting it is really just, there's one way to do that. So for vertical motion, an acceleration function will tell you how the velocity of an object is changing with respect to time. And this part can be confusing because acceleration and vectors, or excuse me, and velocity are both vectors. So we have to take into account the sign or the direction for each of them. So this is explained down here, but it is kind of tricky. So I do want to make sure that you guys pay attention here. So the sign of the acceleration function can't be interpreted on its own. So to say that it's negative doesn't really hold much weight, because to really describe what the object is doing, we need to know um, what the velocity sign is as well. So if the velocity and acceleration functions agree with each other in terms of their sign, so both positive or both negative, then the object is actually speeding up in that particular direction. So if I had an object with a velocity, let's pick a number here. Let's just say after 3 seconds, its velocity was -5. And at that same time, its acceleration was -2. What this means, again, in units, this is feet per second, and this is feet per second squared. So if I was describing the motion of this object, I know that at t equals 3 seconds, let's say my object is up here, my velocity being -5 feet per second is saying that at that exact moment in time, imagine I took a snapshot of a ball dropping. At that exact moment in time, this object had a velocity vector that was saying it is moving downward 5 feet every second. Then our acceleration vector is saying that at that same time, because this acceleration is also negative, every second that passes, this gravity is going to pull that object down and make it travel faster and faster in this negative direction. So at this exact moment, the velocity is pulling down 5 feet per second. But if we were to continue at that same rate, another second passes, now it's going -7 feet per second, and then -9, and so on. So that's the idea. When these agree in sign, the object is going to be accelerating or speeding up in that particular direction. Now, if they do not agree with each other, so one is positive and one is negative, so let's say, for example, I flip this around and make this a +5 velocity, well, that would mean that this object is actually traveling on its way up, but it still has a negative acceleration that is kind of counteracting against it. So every second that passes, that negative acceleration vector is going to cancel out part of that velocity. That is what happens when objects travel up away from the Earth. They slow down, and as they do, my velocity is greater than 0 this whole time because my position is increasing, but my acceleration is actually negative that whole time. So because they're counteracting each other, it's like the negative acceleration is eating away at that positive velocity until eventually it reaches a velocity of 0 at this peak. But after that, when the object is traveling back down, now they are agreeing in sign. Traveling down means my position is decreasing, getting closer to 0. So velocity is negative. Acceleration is always negative when we're talking about vertical motion on the Earth. So because they're agreeing, this is where that object's velocity is going to be increasing in a negative way. Or in other words, the object itself is speeding up. It's getting faster and faster the longer it falls towards the Earth. So that's the important part here. So when they agree in sign, the object is speeding up. When they disagree in sign, the object is slowing down. And that's pretty common language when you guys like the way that you have always heard about acceleration in the past. Those are kind of phrases that you're used to hearing, whether a car is speeding up or slowing down. That language is describing the acceleration of the car, not necessarily the velocity. So kind of easy to transition into the calculus realm when we think of them in those terms. All right, so that is vertical motion. Now we're going to take a look at horizontal motion. A lot of these connections are still the same, but the one big difference is with vertical motion, we have these constants of acceleration due to gravity. So when we talk about an object being thrown up in the air or dropped, these are always going to be our constants, those a values in front. And because of those having a real world representation with gravity, the vertical motion problems kind of always follow the same process, and a lot of the equations look very similar to one another. But as far as horizontal motion goes, we're not taking into account gravity because, again, that's a vertical concept. So when an object moves in a horizontal path, we've already seen how we can describe its motion through the vertical stuff, but there's not going to be a typical formula for the position, velocity, acceleration functions when we talk about horizontal motion. A lot of times we refer to this as particular particle motion. We're looking at how a particle bounces back and forth or an object moves on the x-axis, and that's why our position function is represented as x of t. Horizontal, it's easy to translate all of this simply into the x-axis. So we can kind of think about it in those terms. So we're not going to have a pre-cut form for the equation every time. It's really a case-by-case basis. But what is still the same is our position function is still just talking about where the object is at a given moment in time. The only difference now is we are talking about it on the x-axis. So that means that positive values of position represent positions to the right of 0 on the x-axis. Negative values of position are to the left. So a lot of times what we will see happening is we just treat the origin as kind of our starting point. This is where the particle starts, and then we take into account its motion relative to that point. Also still the same, velocity is still the first derivative of position function, but now instead of positive velocity meaning going up and negative going down, we think of it in those terms, but in the x direction. So when we have positive velocity, that means the object is moving to the right, so its horizontal position is getting bigger. And then when velocity is negative, the horizontal position is getting smaller, so we're going to the left. Then for acceleration, same idea. We still have the 3 different forms, a of t, v prime, or x double prime. So for horizontal motion acceleration, it's still going to be that same thing. It's the change in velocity. So it's telling us how the velocity is changing with respect to time. And we actually have the exact same rules about whether the particle or the object is going to be speeding up or slowing down. It's still all relevant to the sign of velocity and acceleration and how they compare to one another. So that part's going to be the same whether it's vertical or horizontal. So then the only other quantity here we got to talk about again is speed. So we mentioned this earlier. Again, the speed of an object is equal to the absolute value of its velocity at a given time, because again, speed is just the magnitude. We don't care about the direction. We just want to know how fast is the particle or the object's position changing. So we don't care about the direction it's doing it in. We just want to know how quickly is it moving from one time to the next. So for speed, when we think about how speed changes, speed will increase, or another way of saying speeding up, when velocity and acceleration are both positive or both negative. So that's reiterating this point. Speed decreases when the velocity and acceleration have different signs. So that's reiterating this point. So it's just another way of saying or describing that acceleration of the objects, but in terms of just simply speed and not necessarily the velocity. So now that we've talked about everything, now we're actually going to dive in and try some of these examples. So for this first guy, it says a billiard ball is dropped from a height of 100 feet, and we want to write the equation for its position at time t measured in seconds. So then we want to find its velocity after 2 seconds of flight. So because we're talking about an object being dropped, we know that this is vertical motion. Because we know it's vertical motion, important things to remember is that a value is needed here. And to tell which one we're using, we need to look at the units. As soon as I see feet, then I know that we are working with negative 32 feet per second. And since the a values are constants, if you look at the formula, remember it's 1/2 of a. So when we're doing it in feet per second, that 1/2 of negative 32, when we go to write our position function, it's actually always going to start off with negative 16 t squared. If this was in meters per second, oh, I'm sorry, forgot the squared part. If this was in meters per second squared, then it would be half of negative 9.8, so negative 4.9 in front. So you'll see that quite often. Every single one of the vertical motion problems for position, it'll either have negative 16 or negative 4.9 out in front once we do that simplified. But now I need to add in my V naught. So when we say that it is dropped, remember from earlier, that means our initial velocity is 0. So 0t means I don't need to write it. And then it's dropped from a height of 100 feet. So that is my initial height or initial position. So that is actually like the y-intercept of this quadratic function. So along those lines, just to help you guys understand this, it's important to note that this is a quadratic function because that's a special pattern that's going on in the functions here. But where some misconceptions lie is a lot of these vertical motion problems, you guys will see pictures drawn about someone throwing an object up in the air and it goes up and it comes back down. And a lot of times when we do that, it tends to kind of look like a quadratic function, but it's really important to know that these functions for position, if you graph these equations graphs, they do not actually create the path of the object. There are equations in physics that you can create to create the path of an object that is launched. Those require some trigonometry to figure out the angles and everything of the launch. But this equation is not drawing the path of this object. We simply draw this in these sketches to help you guys visualize the idea that the object has to go up and it comes back down. And oftentimes when you throw objects up, they don't go perfectly vertical and straight up and down. They do move laterally some, but that doesn't mean it's always going to be the graph that is created by this position function. So I've got this little thing here. This is from an activity from another class, but it does kind of help you guys visualize what's going on. So I'm dropping a watermelon or I'm not. Dwight Schrute is dropping a watermelon off the top of an office building. And what's happening is this watermelon, if you look at it really carefully, it's actually speeding up as we drop, and that's the idea of that acceleration. So this graph that is created, this is actually the graph that is mirroring the height of the watermelon as it falls. So you can see that those two are perfectly linked together, but the graph is tracking it over the amount of time that has passed as it falls. And so when we do that, when you pair the height of the object in free fall with the time that has passed, that relationship is what creates this quadratic pattern. It's not the path of the object that's creating that pattern, okay? Another example here, if I throw it up in the air, the height goes up and comes back down, and it's still speeding up on the way down. You can see a little bit more of that parabola. So again, I just want to reiterate that this is not the same thing as creating a graph for the path of the object. These equations are representing just the pattern between the height of the object and the time that is passing, okay? So we have our position function. Now we want to find the velocity after 2 seconds. So that would be v of t or s prime of t. So we just do our calculus now. So I get negative 32t. The constant disappears. So velocity at 2 seconds would be negative 64. And then always make sure that we have proper units on here. So this would be negative 64 feet per second. So just from that value, what I know is this one's not going to be totally eye-opening because we're told that it's just straight up dropping off of the building. So we're not launching it this time. We are just standing up top, just like the watermelon, and dropping it off of the roof. But because that velocity is negative, I definitely know for sure that that object is going down towards the ground. Okay. Now, for the second part here, I want to know how long will it take for that billiard ball to hit the ground? Well, saying something hits the ground is like saying its position is equal to 0. So that means I need to set the position function equal to 0 and solve that equation. So I got a good old quadratic equation, but the linear term is missing. And if you guys remember, when the linear term of a quadratic is missing, that means we can actually try to solve this using square roots by isolating the quadratic term. So I'm going to get the t squared part by itself. So if I subtract 100, oh, forgot my negative. And actually, so we could subtract 100 and then divide by negative 16, but I'm actually just going to move this guy over. That'll solve the issue. So we've separated. Now I'm going to divide both sides by 16. And I get t squared, let's reduce that guy, equals 25/4. Square root both sides. Now, normally doing that yields a positive and a negative version of this answer of 5/2 or plus or minus 2.5. But we don't care about negative times. A negative time would mean 2.5 seconds before I dropped the billiard ball. Well, presumably 2.5 seconds before I dropped it, the ball was still in my hand. And I don't care about the motion of the object before it is released. So there are lots of these situations where we end up with extraneous solutions. So we just have to ignore the ones that don't make any sense to us. So in this case, the only meaningful solution is 2.5 seconds. So that is how long it takes for this ball to actually end up hitting the ground. If I start at a height of 100 and drop it, it takes 2.5 seconds to hit the ground. So if that's the case, now I want to find the velocity and acceleration at that time. So now we're just going to take 2.5 and substitute it into our velocity function and then our acceleration function. So v of 2.5 would be, and again, I'm just going to take my velocity equation from the previous part, substitute it in here. So I get 2.5 times 32 would be 64 plus 16. So we get negative 80 feet per second. So that is how fast we were traveling. So now for the acceleration, we just take the derivative of the velocity function. But another thing to keep in mind, because this is vertical motion on the Earth, we should never really have to do the calculus. You can still do it, but it's important to remember what we talked about at the beginning, and that's the force of gravity is a constant acceleration on Earth. So whether we are in feet per second or meters per second squared, it's still going to be constant. It's just a different constant within those different units. So in this case, I can do the calculus of find the derivative of negative 32t, or I just simply remember that that is the acceleration due to gravity on Earth. So we get negative 32 feet per second squared. And again, it's a constant value. It's always going to be that no matter where we are, no matter what the position, no matter what the velocity is, the acceleration due to gravity on Earth is always negative 32 feet per second squared. So we don't even have to worry about plugging in the value of 2.5 because it's always going to be that value. All right, and then one more for this. So let's suppose the ball was instead thrown upwards. So instead of just simply dropping it, now we're going to go up. And again, I'm going to sketch this, but this is not drawing the path of the object, just trying to get you to understand what's going on. So if I throw it upwards to start, that object is going to have a positive velocity initially because it's going up. The height is increasing if I throw it upwards. But eventually, because of the negative acceleration counteracting that positive velocity, it's eating away at it. It's taking away 32 feet per second every second that passes. Eventually, at some point, we will have a velocity of 0. That's when we reach our maximum height. And then velocity continues to decrease 32 feet per second every second that passes. And that's what turns the ball around and makes it come back down to the Earth, because when the velocity is 0 and I take away that 32 feet per second, now I have negative velocity, and now the object will be heading downwards. Okay, so let's keep all that in mind as we build this equation. So we got an initial velocity, that's my v naught of 80 feet per second from an initial height, or s naught, of 100 feet again. And so we're going to build our position function. So really, the only thing that changes now is now I'm going to end up with that linear term. I still have half of negative 32 t squared, but now I have plus v naught t, so plus 80t, and then plus my s naught still of 100. Okay, so that's my position function. And now I want to know, is the ball slowing down or speeding up at t equals 2? Well, this is a matter of acceleration. So remember, this is a matter of comparing the signs of v of t at 2 and a of t at 2. Well, you know what a of t at 2 is. Again, the constant acceleration due to gravity is always negative 32. So I know that this guy is negative. So for it to be slowing down, the velocity would have to have a different sign, or a positive velocity. If this was a positive velocity at t equals 2, then the object would be slowing down because the gravity would be eating away at its velocity and we'd be heading towards 0. But if it's also a negative value, then we're actually speeding up, because that means I'm getting more and more negative, so I'm traveling faster in that negative or downward direction. So that's what we need to answer. We need to know the sign of v of 2. So let's find, not v prime. Let's find S prime, or V of t. So V of t would give me negative 32t plus 80. And now we want to substitute t equals 2 in there. So that would give me negative 64 plus 80, or 16. So if my velocity is still positive, 16 feet per second, that means that this object must still be on the way up. So it's somewhere on its upward travels, and we do not yet have a velocity of 0. So in that case, this object is actually slowing down. V of 2 is a positive value, so positive velocity, negative acceleration counteract each other, and the object is slowing down. All right, same question, but now it's talking about when it hits the ground. Well, we can answer that without doing the math because of what we know about the little bit of physics we've talked about so far. If the object hits the ground, we know two things to be true. It was traveling downwards right before it hit the ground, so that tells me the velocity is negative. And because it's traveling on the Earth, we know that acceleration is always negative, less than 0, always negative on Earth. So because of that, we know that their signs would be in agreement with each other. So I know for sure that that object is speeding up at that moment in time when it hits the ground. Now, if it had asked us to figure out the exact numbers, then we could go through and basically do it exactly the same way. But first, we'd have to figure out where it hits the ground. So we'd have to set the function equal to 0, do a little bit of factoring to solve that guy, or quadratic formula, and then take those values of t and substitute it in like we did with 2 here. We don't need to do that here to answer this question because we know a little bit about the physics involved with this object falling to the Earth. All right. So then the last little bit, so just kind of a warning, not a warning, but just a heads up as we go through this process and we start to look at more real life quantities. So it's really important for us that we can interpret with proper units the value of any function put in front of us, no matter what quantity it represents. And the most important thing to remember is that a derivative represents the ratio of the change in your output variable and the change in your input variable. So whether that's y and x, or the amount of water that is in a barrel against the amount of time that is passes, or the temperature of an object as time passes, or the height measured in feet of an object over the amount of seconds that have passed. Whatever those units are, it's really important that you guys keep in mind that every derivative's value is a ratio of those two quantities. So every single one of your derivative values from now on, when we're looking at real-world problems, should have two units attached to it. The variable for our output of f, or our original function, over the variable of, or excuse me, the units for our input variable on bottom. So it's really important to remember that we've got those proper units, and remembering that it has to be a rate of those two can really help us not go and make any kind of mistakes when we interpret these values.